My name is Wenrui. I'm from Institute of Computing Technology. In this paper, we propose diversity-measurable anomaly detection framework to address the big challenge about the trade-off between reconstructing diverse normals and detecting unknown anomalies. The key is to find a proper measurement of diversity that is positively correlated with the severity of anomalies. We therefore model normal diversity strictly with the suppression to undesired information, so that we do not need to fight against imperfect reconstruction of normals or undesired reconstruction of anomalies, because they can be detected more accurately by the diversity measure together with the reconstruction error. Specifically, we estimate multi-scale deformation fields from reconstructed reference to the original inputs. This model and measure the geometrical diversity to implement above framework. Reconstruction-based anomaly detection model achieved their purpose by suppressing the generalization ability for anomalies. However, diverse normal patterns are consequently not reconstructed well. We show an intuitive case in the last two rows that the severely deformed normal sample 7 has even higher reconstruction error than the abnormal sample 4. This is also known as anomaly-like samples. Although some efforts has been made to alleviate this problem by modeling sample diversity, they suffer from shortcut learning due to undesired transformation of abnormal information without any constraint to the diversity. The toy experiment on MS shows that memory network without diversity modeling cannot guarantee the intraclass reconstruction quality, which misdirects the model to obtain average memory with fuzzy reconstruction and lower discrimination ability. In contrast, the diversity modeling where skip connections suffer from shortcut learning and reconstruct anomalies successfully, which weaken the ability to identify anomalies. Here we introduce the most important issue, trade-off between reconstructing diverse normals and detecting unknown anomalies. To address this issue, we model the principal diversity pattern that positively correlated with the severity of anomalies. With such a modeling, the diverse normals will cause slight reconstruction error and low uncertainty, while anomalies having relatively large score of the measurements to the diversity. Besides, abnormal information from contaminated data is also tend to be modeling with the diversity branch, whose measurement is positively correlated with the anomalies. The corresponding optimization of diversity modeling has three objectives according to the formulation. Firstly, second model diversity from prototypes to any normal inputs that do not yield high scores. Secondly, the diversity generated by psi is positively correlated to the measurement. Finally, as a supplement, psi should include minimal prototypical information. We further apply the framework with geometrical diversity, which based on assumes that anomalies can be represented as significant deformation of appearance, including positional changes and fine motions. In contrast, diverse normal samples can be represented as weaker deformations that's easily distinguished. The model includes two branches for geometrical diversity and prototypical content. With this architecture, we essentially decouple the deformation from class prototypes and make the final anomaly score more discriminative. Inspired by deformable convolution, we estimate deformation fields with k equals to fine scales to model the motion, behavior, and effects of different anomaly types from the reference to original inputs. To avoid shortcut learning by minimizing the unconstrained reconstruction loss, we additionally compute smoothness loss via gradient operation and strength loss. The information compression model uses weaker layer with single memory rather than the linear combination to exclude abnormal patterns. Finally, the binary mask is introduced to separate background information from prototypical memory. For feature space reconstruction, we additionally estimate the reverse deformation process. This allows for applying cycle consistency constraints to alleviate overcompression and address shortcut learning. Finally, we adjust the deformed anomaly map back to the original position for the localization task. Here we have two toy experiments on MNIST to illustrate our work qualitatively. The cross-to-find deformation fields are shown as trans C and trans F on the left, and the middle lines on the right. The measurement to the geometrical diversity is shown as ADF, and the final anomaly map is marked as score. And our approach outperformed previous work on both video anomaly detection and industrial defect detection. The visualization results show significant difference between diverse normal and abnormals, and shows the effectiveness of binary mask in Shanghai Tech datasets as well. Unlike PDM, PPDM is partly in charge of the information compression. That is, PPDM removes the diverse appearance by using the reverse deformation process. In conclusion, Diversity-Measurable Anomaly Detection Framework models restricted diversity and achieves better trade-off between reconstructing diverse normals and detecting unknown anomalies. As an implementation of DMAD, pyramid deformation module performs diversity measure that's positively correlating to the abnormalities. The results on both video anomaly detection and industrial defect detection shows the effectiveness and applicability of our work.